Good evening, everyone. Am I audible?
Yes, sir, you're audible, sir.
Before we start today's class, is there any doubt or anything you want me to discuss or address? Okay. Shravya, what group are you referring to?
So this was regarding some of the question asked for the WhatsApp groups.
Okay. So today there were few questions that were left out in the last class. We are going to solve that. But first, let us try to solve these three problems. So the first problem is we are going to add the following components from the Aspen Plus data bank, that is acetone, MEK, that is methyl ethyl ketone and hexene. And using the NRTL property method, we are going to generate the TXY graph for hexene and MEK at 25 degrees Celsius and 30 degrees Celsius. So before doing this simulation, I just wanted to ask, like, what is the basic knowledge that you all have regarding binary analysis of components? So what do you understand by binary analysis? Where is it used and how is it determined, etc., etc.? Anyone?
Interaction among only two components that we have learned earlier.
Okay, so what are these interactions mainly?
So what are their properties among them? So like we have generated in the first lecture, enthalpy, entropy. What are the all that things?
So, like, usually, when is it used? Like, in what processes are they mainly used?
So like I can't say process, but like we have done flashing of two vessels. In that we have used the binary in the last lectures.
We usually study interaction of two or more components wherever we want to separate them. Okay, we want to know whether the separation is possible or not, or to what extent is the separation possible. In that case, we usually study the binary analysis or the tertiary analysis of components that we have for our system. So, binary analysis, the best example for binary analysis can be flashing of two components is one example. The other very prevalent example is that of distillation. Like we must have read about the pressure pxy curve and txy curve we usually generate before performing a distillation process. It actually gives us an idea, as in if we are operating the distillation column at a particular temperature, then what is the extent to which two components, let's say x and y, and let's say two components c1 and c2, and to what extent these components can be separated, and what will be the maximum purity that we can achieve at that particular operating conditions. That is for binary analysis. And for tertiary analysis is when there are more than two components. In that case, the best example is that of extraction, where we have a solution and the solution is made of two components, say A and B, in which we use a third component, C, and we see how these three components interact with each other. Usually, the component C that we use, it is miscible or with one of the components A or B, and while it is immiscible with the other component in the solution. In that case also, we have a few terms like azeotropes, and that is the extent to which the separation is possible. And in extraction, we get in the for three components we get more than one azeotrope, but in binary distillation we usually get a single azeotrope. So to begin with, the problem that we have at hand is we are going to use these three components. So first, let us write down the component names.
Say for example, if two components are reactive among each other, then we will not use all this only purpose.
Reactive among each other. What do you mean
Yes,
by reaction?
means means acid plus base. Sometimes they make salts and all that. If they are too reactive, then can't we use binary in that?
Acid and base.
Or acid or water.
The example which you are giving, as in like acid and water, is if we mix both of those two components, then that process becomes dilution, right? We are diluting the acid in that case. These analysis are usually used when we want to se- aim for separation. For example, we have ethanol and water, right? We know that ethanol water mixture or a solution, it forms an azeotrope. Like to an extent, we can separate it. So what is that extent to which we can separate, and at what concentration, that the maximum concentration we can obtain through the separation, that we can get to know from the binary analysis. And as far as reaction is concerned, then yes, you can say reaction in the sense like if we mix two components, let's say ethanol and water, so that solution, whether it's an that mixing process, whether it's an endothermic process or an exothermic process, because sometimes mixing process does generate heat. So that is the extent of like reaction that takes place in such scenarios. First we have acetone, next we have methylethyl ketone. Hexene. Now the property method, you can use NRTL, or you can select any suitable property method from the property method assistant, which we have discussed in the previous classes. So let us stick to the property method that they have given to us in the question. Now when we are going to click on next, you can see that we have a total of 3 components, but the binary interaction of only 2 components are given to us. Okay, so we need to have the interaction of all the 3 pairs. So the missing pair we can estimate using unifact. All of this we have discussed in the previous classes already. So now we are going to run the property analysis and setup. So here you can see that the missing interaction was evaluated using this regression model, and the interaction parameters are generated. Now, how to determine its binary interaction? Anyone?
Binary interaction means it's nearest boiling point.
Yes, I'm
Mixture of
asking.
many.
I'm asking through Aspen, how can we do that?
So on the right hand side top, we have this binary in analysis tab.
Right. So using this, when we select this tab over here, so here you can see the analysis type that we want to do. So there are a total of this. There are multiple analysis that we can perform in the binary analysis window. So the analysis that we have been asked to do is TXY graph. So we are going to select TXY graph. There are 3 components that we have. So we are going to select 2 out of them. So over here, acetone and MEK is selected by like previously. So if you want to change, you can change it from here. So let's say I want to see the interaction of hexene and MEK. So over here, the component that is varied is usually the component 1 that we select over here. So over here it is being said that we are going to change the mole fraction of hexene, and the basis is going to be mole fraction, and the starting point is 0, and the maximum mole fraction that we can get is 1. There are 2 ways we can we can specify the intervals. That is, either we can see how many points we want, or we can select the intervals. So let us select this interval. It is given 0.01. Let me just change it to 0.1, 0.02, it is, let me change it to 0.1. Next is we are performing TXY. So can anyone give me a basic definition? What is a TXY curve?
It gives the equilibrium between vapor and liquid at different temperatures and constant pressure.
Okay. So the very important aspect over here is we have to specify the pressure at which we want the TXY curve. So over here, the unit is given bar. If we want to change the unit, we can change it from here. So if I specify that we want the temperature, the analysis to be performed at 1 atmospheric pressure, we can change it like this and then we can run the analysis. So once we have run the analysis, you can see that a graph is generated. Over on the y-axis, we have the temperature in degrees Celsius, and on the x-axis is the concentration, constant mole fraction of hexene. Okay, so this is the TXY diagram of hexene MEK solution at 1 atmospheric pressure. So what is the boiling point of this mixture? These are the few things which you need to understand from the graph. Like after generating the graph, these are the few basics that you have to understand. Like what is the graph and how can we visualize it and what is the data that we can extract from it.
Boiling point of the mixer is 79.58. So
It is between 79 to 80. Okay.
yeah,
So this green uh, square, it indicates the mole fraction in the vapor phase, and this X, it indicates the mole fraction in the liquid phase. So this becomes our bubble point curve. That is the one that is uh, given in color blue, and this becomes our dew point curve. I hope everyone remember the definition of dew point and bubble point. Okay. So usually how we visualize this curve is, let's say if we have now, you will be wondering that only if there is a mixture of two components, then why only one component is required. Like we know that from this mass balance, if we have two components, let me name it as C1 and C2, and we have the mole fraction of one component which is equals to x1, then the mole fraction of C2 can be evaluated as 1 minus x1, since x1 and x2 will be equal to 1, since there are only two components inside the mixture. Okay, so now remember that the system is operated in a constant pressure. So over here, P is equal to 1 atmosphere. And this is the saturated liquid curve, that is the boiling point curve, and this is the saturated vapor curve, that is the dew point curve. Okay. The space in between is the place where both the this is the place where liquid and vapor mixtures coexist in equilibrium. So if you are given a particular mixture which exists at this point over here, that is 0.25 of hexene and 0.75 of MEK. Now keeping the temperature or keeping the pressure fixed, okay, if we increase the temperature, then it is going to move upwards. Then this is the point at which you are going to get the saturated vapor, that is at 74 a temperature that lies between 73 and 74, and the corresponding temperature of the uh, temperature of the mixture will be obtained from here. Similarly, if we cool down, so the temperature is going to drop, and at this temperature we are going to get the get the saturated liquid or the boiling point of the mixture at 1 atmospheric pressure. So this is how these graphs are interpreted. Now this becomes our TXY plot. The other plot that we can generate is the PXY plot. Now in PXY plot, the situation remains the same. Only the thing changes is over there we had specified the pressure of the system. Over here we are going to specify the temperature at which we are going to generate the PXY curve. So over here the PXY curve temperature is given 25. If you want another temperature, let's say 30, you can add it over here. And then you can run the analysis. So over here you can see that two graphs are generated, and the legends indicate that the mole fraction and in the liquid phase and the mole fraction in the vapor phase for hexene at the two different temperatures, that is 25 and 30 degrees Celsius, are plotted over here. Now in this case, can you tell me which one is the dew curve and which one is the bubble point curve?
Blue is the dew point curve, green is a bubble point curve.
Yes. So over here you can see that the orientation is just has reversed. So from this curve over here, can you tell me whether 100% separation is possible or not?
No,
Okay, till what purity of hexene can we separate?
0.7.
So over here you can see that this dew point curve and the bubble point curve, they actually merge at a particular concentration of hexene. So this point over here is the azeotrope. Over at this concentration of hexene and MEK solution, that is 0.75 of hexene and 0.25 of MEK, we will get the azeotrope, and the corresponding uh, pressure is that of zero point 0.3. So at this, beyond this point, separation is not possible. So this is the point of azeotrope formation. We have other analysis types also, that is TXX. So in that case, we have to specify the key components over here. That is, if TXX is usually used for vapor liquid-liquid equilibrium. The previously we had vapor-liquid equilibrium. This is for vapor-liquid equilibrium. Similarly for TXX, there is TXXY and PXXY, and also Gibbs energy of mixing. Okay. So these are the multiple analysis types that what binary analysis of Aspen provides. So is there any doubt from this particular question? Okay. So the next question that we are going to solve is, we are going to consider, previously we have considered binary analysis. We have three components, out of which we studied the interaction of MEK, and we did the analysis of MEK and hexene. So in this, we are going to consider three components. So the ternary mixture of three components that we are going to consider are ethyl acetate, ethanol, and water, and the pressure is 101.325 kilopascal. We have to find all the azeotropes of the mixture using this property method in our TLHOC model. We are going to specify the type of azeotropes and the singular points that occur in this mixture over here. Next is, we are going to draw the distillation boundaries and residue curves for this ternary mixture. So try to do this. Over here, what we are going to do, previously we did binary. In this case, we are going to do ternary diagram. Okay. So use this tab, enter all these components over that I have mentioned over here, and try to see whether you can solve these three sub questions with using that ternary option. Try to do it for, take 5 minutes to do it on your own, then I'm going to show you how to do it. Has anyone been able to do it? Method name that is given to us is NRTL HOC. Click on next. So these are the interaction parameters for ethanol, ethyl acetate and water. I'm going to click on next again. So this is the interaction binary interaction parameters for NRTL for the three components. So over here you can see all the interaction parameters are retrieved from the data bank. So over here we don't need to estimate any missing interaction parameters. So we are going to click on next and we are going to run the property analysis. So once that is done, we have to go to the ternary diagram. So whenever you select ternary diagram, you're going to get a dialog box like this over here. So I would suggest you that you do not check this button as do not show me this recommendation again. It is better to have this dialog box so that you can access these many options over here. So we are going to look at all the uh, analysis options that we are going to get over here. So first is we are going to find azeotrophs. Next is we are going to use the distillation synthesis ternary maps. And the last is we are going to, there is one called continue to Aspen plus ternary diagram. So first is we are going to find azeotrophs. Okay. So over this dialog box, what is given to us is we have the component list. These are the components that we have entered through the Aspen data bank. The pressure is also mentioned to us. The property model is given and the phases that is given to us. Okay. So over here in phases, there is vapor liquid and vapor liquid liquid. Okay. The pressure is also given. So at what pressure do we have to do is 101.325 kilopascal. So this is the pressure we don't have to change. And the component list, we have to check all of them. Okay. Now that we have done it, what we have to do is we have to click on next. Okay. So over here, these are the pure component datas. So the component ETA, ethanol and water, the boiling point of these three components are given to us. So water is at 100 degrees Celsius, ethanol is 78.3, and ethyl acetate is 77.2. And you can see the classification as given as stable node. Okay. So can anybody tell me that what is the meaning of a stable node? This classification, what does it signify? You can give wrong answers, it's not a problem. I just want to know like what you understand, because Aspen is a very direct software. Whatever input you are going to give, it's going to give you the output based on the calculations that is happening at the back end. It's like a black box software. So you need to understand like whatever the data that you are seeing on the screen, you need to be able to interpret it. That's why I'm asking all these questions.
Steady state condition.
But we are not conducting any process over here, right? So why is steady state coming into the picture? Steady state usually we like the steady state term is usually used in reference to processes, in which case the observed variables, that the variables that you are considering, they are not changing with respect to time. In that case, that process is said to be in the steady state. So for example, if you have a heating tank and you are heating the tank, but the temperature that you are measuring, it has reached a particular value, and for a time period that value is not changed. Condition 2, the system is also not disturbed. So that is the state at which we tell that the process has reached a steady state. But over here we are doing analysis, right? So over here you have this table and it is giving you three components, and the temperature of the three components are given. And there is one another column which says classification, and over there only stable node is written. So my question is what to infer from this classification, like why stable node is written over there.
That is a phase change from the liquid to vapor.
So like if liquid to vapors, but phase change, will that be a stable node if change is taking place?
At the critical temperature and pressure, it will be stable condition.
The correct term that you can use is it is a point of equilibrium. A point of equilibrium means that at these are the boiling points that are given. Okay, so if you are not heating the system or you are not disturbing the system and you are keeping the system at that particular pressure, that is 1 atmosphere or 101,325 pascal or 101.325 kilopascal, then the boiling point of these components, they are fixed. Okay, and the fact that these are stable nodes is that there won't be any deviation from these points. Remember that whenever we are plotting a binary, when we are doing a binary analysis or a ternary analysis, we are usually interpreting graphs which give us values in terms of pressure and temperature. And whenever we are going to like traverse through the graph, it will be in terms of temperature or pressure, right? In this case, we have fixed the pressure and the temperature is going to vary. So what this particular table is trying to tell us that if we are keeping the pressure fixed, then these are the particular boiling points of the components, and these points are not going to deviate from that particular value that is shown in this table. So that is why they are called stable node. Although if we change the concentration of the other components inside the ternary solution. Now coming to this next point over here, we are going to get azeotropes. Okay. Now these are the temperatures at which azeotrope is formed. Okay, and the concentration is also given. The concentration at which these azeotropes are going to form. Now over here, you can see that there are classifications of saddle, unstable node, and the other two azeotropes are called saddle classification is given. Okay, I'm going to tell about this classification of saddle and the stable node we have said, the unstable node I'm going to tell. Now over here, can you tell me what does homogeneous azeotrope and heterogeneous azeotrope mean?
Hello.
Homogeneous or miscible liquid mixture.
Homogeneous or, can you please
Miscible
repeat?
liquid mixture.
Miscible liquid mixture. Okay, and what will be?
Heterogeneous is a invisible.
Yes, you are right. So we can also define it as like a homogeneous azeotrope. We are talking in terms of azeotropes, right? So, in the previous binary analysis, we have seen that azeotrope is a condition beyond which we cannot perform further separation. Okay. So, in this, homogeneous azeotrope is a azeotrope in which the azeotrope formed at that particular operating conditions, they remain in a single phase. That is, they do not separate into two different phases. These two different phases can be in vapor liquid, or it can also be in liquid liquid. So if we have the best example is that of ethanol, water and methanol mixture, they form a homogeneous azeotrope in which all the components mix completely in a single phase. That you can't differentiate the components with your naked eye. That is, if you look at a container that has all these three components, they will appear as a single liquid. But in case of a heterogeneous azeotrope, they lead to a liquid phase separation, that there will be some separation which you can understand. So either some vapor might be formed on the surface of the liquid, or two-phase liquid will be formed, something like that. So it becomes a heterogeneous azeotrope. Or to speak specifically, that the system, it separates into two distinct phases at equilibrium, that is at the operating conditions where the azeotropes are formed. The example for is a water, ethanol, and benzene mixture. Okay, so the previous was ethanol, water, and methanol, but this one is an water, ethanol, and benzene mixture. They form a heterogeneous azeotrope. Now, the reason why it is because benzene, it helps to remove the water from the ethanol because they form a ternary azeotrope at that particular point. So that is why two liquid layers are formed. Now, these situations usually happen whenever we handle like three components in which one is more miscible with the other. So naturally, they combine together. There a density difference occurs, leaving out the third, and a separation is clearly visible to our naked eye. So that is when an heterogeneous mixture or a heterogeneous azeotrope is formed. Okay. Now coming to the classification of saddle points. So how to define a saddle point is, previously we had seen in binary analysis that in a graph those boundaries are formed that are called the bubble point curve and the dew point curve, which signify us about the temperature or the pressure at which we are going to get a saturated liquid or the saturated vapor of the mixture that we are handling. Those curves, they also give us a, or they are also called the distillation curves. That is the separation or the concentration at which our components will get separated when we are operating from a particular temperature, either heating it or cooling it, or if we are changing the pressure. Okay, so a saddle point in a ternary diagram, it actually signifies a point where distillation boundaries intersect. Okay, they are usually points of unstable equilibrium. Like previously we had studied about stable points. Over here, these saddle points, they are actually unstable equilibrium. That is this mixture, whenever we try to like converge our operating conditions towards these particular points, they try to deviate. That is, they shift towards a different stable composition. So let's say over here you had this 78.3 is a stable node over here, while this 78.154 is a saddle point. So whenever we are trying to go towards this point of azeotrope, the point is going to move towards this temperature of 78. Okay, but that doesn't mean that we are going to get a efficient separation out of this process. And they usually take place in case of ternary, like as your ternary mixtures only. In binary conditions, we hardly see any saddle azeotropes forming. Okay, so this is what it is. And in unstable node, it is a composition like where no separation can reach an equilibrium. We cannot have any equilibrium points at an unstable node. Okay, so if you see properly that in a saddle node over here only two components are there, whereas an unstable node there are three components. So we cannot reach a particular equilibrium when we are at an unstable node. If we are starting from an unstable node, then they are always going to move towards saddle points. That is the only thing that you need to remember in this case. Next, coming to the singular points, then these are the singular points that we are going to observe in the graph that we are going to generate. There are stable nodes, saddle node and the unstable node, and all the point like with pure components and azeotropes that are being formed. Like everything that we have discussed up till now, these are the particular points that will be marked on our graph. Okay. So let us take the ternary diagram again. So over here, let us use distillation synthesis ternary maps. So over here, we have to specify the components. So component 1 is ethyl acetate, component 2 is ethanol, and component 3 is water. This for vapor liquid equilibrium model, we are going to use NaTl HOC. We are going to use the same model for the liquid liquid equilibrium model as well. And the phases are vapor, liquid, and liquid. The basis is going to be mass fractions, mole fraction, and the temperature unit is going to be centigrade. And what are we going to calculate? We are going to calculate residue curves, azeotropes, and distillation boundary. Okay. Once we have done that, if we come over here, so here this is how uh, ternary this is how a particular ternary graph looks like. You can change the orientation. So this is a right angle triangle. If you want to visualize in an equilateral triangle, you can. Sorry. You can flip it like this. So I hope, like, is there anyone who knows how to read these graphs? You can add grid lines from here. Let me zoom it. Let me zoom. Does anyone know how to read ternary graphs? So we had three components, right? So this is the line of ethyl acetate. This is the line of water, and this is the line of ethanol. So how we read ternary graphs is like over here. I think at this point, if you see, you can see that this mole basis like have a note of this part of the screen over here. I'm taking the cursor to this tip. So if I add a marker to this tip over here, you can see that ethyl acetate is 0.002, ethanol is 0.993, and water is 0.005. Now the point that I have selected is not proper, or it's not approximate. That is why the ethanol concentration is showing as 99.3, but it is actually pure ethanol over there. The value of the mole basis value should be 1 for ethanol, for ETA it should be 0, and for water it should be 0. So this is the point where we have pure ethanol. Similarly, if we take the marker over here, you can see that this is the point where water is maximum. That is, this is the point of pure water over here, and this is the point of the remaining, that is we have ETA, that is ethyl acetate. So this point over here, it gives us ethyl acetate. Okay, so ethyl acetate is 99.4 over here. Now, how to read this graphs is like, if we want to plot a point, so how do we do it? We usually add a marker over here. So if I add a marker over here, it is going to give me the concentration of that particular point over here. Okay, so what is the concentration of this particular point? So ethyl acetate we have 0.2%, ethanol we have 0.6%, and water we have 0.2%. Fine. So this is how we read the graph. Uh, Over here we are using a software. Like if we don't have a software and we have to study from pen and paper. So in that case, what we do is, this line over here is water is zero point 0.2, right? So this is actually zero of water, and as we move, the water concentration increases. So naturally we are going to get a concentration of water at this point. Similarly, ETA, ETA is also zero over here, you can see. So as we move upwards, so over here we are going to get ETA. So once we have the concentration of ETA and water, the remaining is ethanol, because it is a ternary component. There are three components over here. So if we deduct the mole fraction of the other two components, we get the third component from the mass balance, or the summation rule, that is 1 minus x1 minus x2. We get x3 from here. Now there are this shaded region, it is actually the liquid phase, and this outside the shaded region is the vapor phase. These are all tie lines, that is, these are equilibrium lines for in the liquid phase, and these are the distillation residue curves over here. So if you recall this 78.15, this is 78.15, it is a homogeneous azeotrope. So if you look at the azeotrope, the azeotrope lines are given over here, as well as the unstable node is given. Okay, the unstable node is 70.33. This is pointed out, this one, 70.328. This is the unstable node of the three components. So if you check that this unstable node, then you are going to get the same concentration that you are going to see over here. And these are the distillation curves. These distillation residue curves, they actually divide the entire ternary diagram into different phases, or sorry, not in different phases, in different boundaries. So the distillation curves over here, they have separated this ternary diagram into three uh, boundaries. This one is one boundary over here, this one is the other boundary, this one is the other boundary. So if we are trying to perform distillation, we cannot cross the distillation boundaries, it is not allowed. So in that case, what we do, we usually integrate a distillation process with secondary separation processes to achieve the desired separation. So for example, if you are starting from this point over here, what you are going to do is you have to reach up to this point. Over here, you can perform some extraction and reach over this point. And from this point, you can again move to this point over here to perform again distillation. Okay, so this is how we usually traverse in a ternary diagram, or this is what a or this is what a ternary diagram signify, that in order to reach from here to here, you just cannot cross from here, but you have to come through this path like this. So which involves an extraction. If you remember, in ternary diagrams, in extraction process which we had learned, we had ternary diagrams and there were tie lines. So this for the liquid phase mixtures, we usually go for extraction. So from here we can perform separation, like we can use distillation and we can reach to this point over here. And by reaching to this point, I mean that through change of concentrations, because from this point, if we're coming to this point, then this point is also going to have some concentration which is being reflected over here. Over here you can achieve better concentration of your key component through extraction. Let's say you reach to this point over here, and from this point going back to this point over here, you need to perform phase change, so distillation can again be employed. So this is how you move from one point to the other. So this is all, and these are all the azeotrope points that are formed. So this point over here, it is the azeotrope between uh, what is this azeotrope? So this is the azeotrope between which components? This point 78.15 degree.
Ethanol and
ethanol
water.
and water.
Yes. So similarly, if this is 78.15 is for ethanol and water, this 71.78 is between ETA and ethanol, and this 71.39 is between ETA and water. Is there any doubt? And also remember that this there is a plate point that exists at the interaction between this vapor phase and this liquid phase over here. It is usually this point over here, right at the tip of the this liquid envelope. Is there any doubts? Anything regarding to this? Okay. As of now, we have always tried to like add components that are already there in our data bank. So over here, we are going to estimate the physical properties of a component for which no data is available in the database of the simulator. If you remember in the previous classes, I had said that I would show you examples where we can add data which are not there in our data bank, or add components which are not there in the data bank. So this is one component over here. Okay, so we are going to see how to add this component in Aspen and how to estimate its physical properties. So let us start. So over here we can name the component. Let's say I am giving my name over here, and the type we are going to use a user defined. Okay. So let me give the name as, and the type, let me keep it as conventional. Okay. I'm going to click on next. Now over here, there are two options that you can do. One is we can draw, import or edit structure, and the other is we can define by its molecular connectivity. So I'm going to show you both. Remember that this molecule structure over here is that of MTB, okay, that is methyl tert butyl ether. We are going to see how to define this in Aspen. So let me start by defining this molecular connectivity. So here you can see that the carbon numbers are being numbered. That is 1, 2, 3, and 4 is the oxygen molecule. Remember that whenever we are defining components like this, we are usually specifying the carbon and if it is connected to any other elements, oxygen, to those, and they have, we all know that they have a particular bond capacity. Like for carbon, there are 4 bonds that can be attached to a carbon atom. Similarly, for oxygen, its valence state is 2, so there are 2 bonds over here. So once we specify this, the remaining bonds, they are actually populated by hydrogen. Okay. So if in case of hydrogen over here, if there was some other element, let's say nitrogen, so we have to specify that that oxygen is connected to nitrogen. Those that we don't specify, the rest of the valence atoms, that rest of the valence bonds, they are automatically filled with hydrogen. So what is over here? It is telling that atom number. So the atom number is 1. What is the atom type? The atom type is carbon. Then we have to specify unique number identifying an atom in the molecule. And what is it is connected to? It is connected to carbon only. So you have atom number 1. What is the atom 2 number? This is 2. And what is this atom 2 type? This is also carbon. Okay. And what is the bond? The bond is single bond. So we have actually specified this part over here. Okay. Next is our atom number is 2. Our atom type is carbon. This is connected to 3. Okay. The atom type is carbon again. Atom 2 type, that is this is carbon. Okay. The bond is single bond. Now note that the second atom is connected to another carbon over here, which is indicated as 5. So what we are going to do is atom number is 2, the atom type is, and this atom 2 number, it is actually 5 because this is going down over here. And what is this atom type? This is also carbon. What is the bond type? That is also single bond. Okay. Now atom 1 number is 3 because we are going to connect these two now. This is going to this atom 2 number 4. Okay. And what is this atom 2 type? This is oxygen, and this is also single bond. Now we have specified this. So over here you can see that 1, 2, 3, that is the number 1, 2, and 3, this is carbon, and this is 5 is also carbon, and 4 is oxygen. Now structure and functional group over here. So over here, how can we these are group contribution methods. So these methods are used to estimate the physical properties. So over here, what we are going to do, there are different group parameters that you can use. So let me use this over here, this paracord group contribution method. For the details about what are these group contribution methods, I would suggest you to study the literature or the help files over here. It will give you a better idea. So over here, I'm selecting this paracore group. Okay. So functional type is, I'm going to keep it as all, and so here I am adding it. Okay. Then we are coming to the formula. So here we are going to select the number of occurrences of carbon is 5 times, and next we have oxygen. The number of occurrence of oxygen is once. Okay, so we have specified it. Now we are going to close this. We are going to go, so over here you can see that structure form was opened. It is better that if we can fill up these forms like these values, but since we don't know, we are not going to do anything. And we are going to estimate using property estimation over here. So we are going to click on finish. We are going to click on OK. We are going to select next. Let us select the method name as NRTL. Now we are going to click on next. We are going to run the property analysis. You can see it is telling that this was not in the data bank. So let us go to this components over here and select this review. So here you can see that these all of these are calculated from the so from here you can see that these values are being calculated using the structural data that we have provided. So CPIG, this is also calculated. The units are given over here. Okay. This is PCS, so the boiling point temperature, the critical temperature, critical pressure, everything is given for this component over here. And the source is also given, that is from RPCES, it has calculated. Since the data was not present inside Aspen initially, so we have defined its molecular structure, and then we have tried to estimate its properties. Is any doubt?
Hello,
Yes.
can we add this component in the data bank?
This component has been added in the data bank. Now you can use this component in the simulation now. Data bank as in you cannot add it into the data bank that Aspen that is provided in the Aspen during its installation. But if you want to specify a particular component, you know about its structure and its chemistry, you can add it in Aspen and you can use it for simulation.
Oh,
Now let me show you how to do it using a mole file. So this is Q3 mole file. Now let me rename this as the same. I'm going to use it a user defined, the conventional type only. I'm going to select next. Now over here there is an option of draw slash import or edit structure. Previously we had defined molecule by its connectivity, in which we had specifically mentioned the connectivity of the molecule through numbering the carbon atoms. Over here we are going to draw or import or edit the structure. So for that what we have to do is we have to go to a website over here. It is called NIST, and we know the molecular name, that is MTBE, and I'm going to write MTBE mole file download. So over here we are going to get this methyl third butyl ether mole file. So if you remember correctly, this is the molecular formula which we had defined. So this is the structure. So we are going to download the 2D structure. So over here you can see that you can download the structure. So if I just click on download, oh, so remember that Aspen is compatible with mol files. Okay, so we cannot download any file format and then ask Aspen to do it. Let me just search for database. Here, MTB. See if this download work. So from this option of draw and import, I'm going to open the file, but it is not supporting that file format. I'm not able to find the mole file of this particular compound, so I'll try to show this in the next class. However, this connectivity is also equivalent to the import of the mole structure. I'll look into this and I'll let you know in the next class. Okay. So is there any doubt up till now, or we can go to the next problem? So this is the problem of an R stoic model. This is for reactor models in Aspen Plus. So over here, what we have to do is we have to convert ethyl benzene to styrene and hydrogen. Okay. So the question says that ethyl styrene is produced by dehydrogenation of ethyl benzene. Here we consider an irreversible reaction given as C6H5C2H5 gives styrene and hydrogen. Pure ethyl benzene enters the R-stoic reactor with a flow rate of 100 kmol per hour at 260 degrees Celsius and 1.5 bar. The reactor operates at 250 degrees Celsius and 1.2 bar. We can use the fractional conversion of ethyl benzene, which equals to zero point 0.8. Using the Prin-Robinson thermodynamic model, we have to simulate the reactor model. So take 5 minutes of time and try to solve this problem. So we are going to start a new simulation. What are the components that we have to add? We have to add ethyl benzene, styrene and hydrogen. So first let us enter styrene. Ethyl benzene and hydrogen. So we name this as styrene. This is ethyl benzene. Now click on next. We have to specify the method name. So the method name that we have to use is Ping-Robinson thermodynamic method. Now we are clicking on next and we are going to run the property analysis. Now come into simulation. Note that we have to use R-stoic reactor. So in reactors, we have R-stoic. What is R-stoic? It is a stoichiometric reactor based on non-fractional conversion or extensive reaction. So what is a stoichiometric reaction? Stoichiometric reaction is when the stoichiometric coefficients of the reaction is unity, that is 1, we call it a stoichiometric reaction. So from the R-stoic reactor, we are going to keep over here. So material stream, it is a very simplified reactor. So this is the feed stream coming in and this is the product stream going out. Now we are going to click on next. So S1 is our feed stream. So we have to give the feed stream. So pure ethyl benzene enters the R-stoic reactor with a flow rate of 100 kilomole per hour at 260 degrees centigrade and 1.5 bar. So this is 260 degrees centigrade. This is 1.5 bar. And the reactor operates at the 100 kilomole per hour. So ethyl benzene is 100 kilomole per hour. Okay. So over here you can see the blue tick, which means that the feed stream is specified. Next, we are going to specify the operating conditions of the reactor. So the reactor operates at 250 degrees Celsius and 1.2 bar. So this is 250 and this is 1.2 bar. Okay. Now, previously we never handled any reaction in Aspen. So we have to specify the reaction over here. So when we are going to click on next, it is going to take us to the reaction page. You can see that no reaction is specified. So we are going to click on new. So this is reaction 1. So what is happening? Ethyl benzene is coming. The coefficient of ethyl benzene is -1 since it is a reactant. The components that are being formed is styrene and hydrogen. The coefficient is 1 and 1. These are products. Next, what we have to do is we have to give the fractional conversion. So the fractional conversion of ethyl benzene is 0.8. So over here, the fractional conversion of ethyl benzene is 0.8 and the component with respect to whose the fractional conversion is defined is given over here. So we are going to select ethyl benzene. So you can see that the required input is complete now. We are going to click on next. We are going to click on next and it is telling that all the required input is complete. And now we are going to run the simulation. So here you can see that the results are available with no errors and warnings. So what is being asked to us? You have to find out the stream results and the amount of styrene that is being formed. So in the mass fraction, you can see the styrene in the product over almost 80% of styrene is formed over here, or 78% of styrene is formed, and 2% of hydrogen is formed, and 0.8% of ethyl benzene is consumed. So 0.2 more or 2% of mole or 0.2% of or 20% of ethyl benzene is present in the result stream. So this is how you can simulate a R-stoic reactor. So is there any doubt? So I would like to end the class now. If there is a doubt, you can ask me.
No, sir.